Welcome all of you for today's live session of Power System Engineering NPTEL course. And this is our second session. And I am Gagan. I am doing my PhD at Electrical Engineering Department, IIT Bombay, in Power System Engineering. So we will start with the session now. This will be the agenda for live session. We'll start with a quick overview of week 2 and then we'll discuss some questions regarding week 2, and then you can ask some questions also, doubts. In between also you can stop me and ask any doubts that you have. These are the deadlines for assignment 1 and 2. You have to submit these assignments before till 7th Feb. So kindly submit on time, and you can also find the recording of these live session on this YouTube channel, the link of which is available on the portal. So on the portal, on the left hand side, you will find a problem solving session tab. In that you will find link for a Google Drive. In that there are links for this YouTube recorded lectures as well as the presentation which I am using. So let us start with a very quick overview of week 2. So in week 2, the entire week 2 was dedicated to the underground cables, which we studied. So different types of cables were discussed, and then the most important one thing in cable is insulation, which is required to cover the conductor of the cable so that they can isolate the conductor from each other and also from their surrounding. So all the insulating materials which are used, they should have very high dielectric strength, high insulation resistance, which we also calculated. The formula of this was rho 2 pi L ln R by R. This is the conductor radius and this is the radius plus thickness of the sheath which is used. Then it should have good mechanical strength. And it should also be able to withstand temperature from different degrees, from -30 to 100 degrees Celsius. Then we discussed different types of cables like vulcanized Indian rubber cable, and then elastomer insulated cables, then PVC cables and polyethylene cable. Then also is XLP, cross-linked polymer polyethylene cables. So out of these, the XLP is very advantageous because it has lightweight and overall cable dimensions are also small. And it has low dielectric constant. As well as good mechanical strength. And also it can operate in temperature ranges of 92 to 50 degrees Celsius, which is very good. And these cables are suitable for use up to 33 kV. So we will find most of the usage of these XLP cables is in distribution system up to 33 kV. Then next one was the paper insulated cable, which is the most widely used cable, and paper is the most important insulating material which is used in the cables because it is very lightweight. It has ability to withstand high temperatures. It is also very durable and has very low cost. and superior heat conductivity, as a result of which it is very conducive, very good for material, insulating material for cables. Then we discuss that what are the different components of a cable. Apart from insulation, sheath, armor and covering. These are the three main components. So do you remember why sheath was used? What is the usage of sheath? Do you remember? Any of you people, do you remember why sheath is used? Sorry, I'm not able to hear you. Just a minute. Yes, people, can you speak again?
No, I think sheath is used to protect the conductor like that will not act any type of chemical reaction from the soil, I think.
Yes, that is correct in one sense. So that is true. It is provided over the cable, so cable is covered. This conductor over which we have insulation, so that is covered, so that moisture may not be able to affect the cable. And it also protects the insulation from the mechanical damage, because insulation is very important. Suppose in one cable, so if a 3-phase cable is there and we have 3 conductors in the same cable, then if insulation is not there, then these 2 conductors will touch each other and there will be short circuit. So insulation is very important, and to further protect that insulation from any kind of moisture or chemical reaction, sheath is provided. So it further helps. It strengthens the insulation, I can say. So this sheath is it has a thickness, it's quite thick. So it helps to prevent that damage from moisture and chemical reaction. So that is why different type of metals are used. For example, lead is very common. An advantage of lead is that it is easy to manufacture them and they are very flexible and have also high corrosive resistance. So we need the metal which does not corrode easily, otherwise its life will reduce. But there are some disadvantages also. Lead has a high density, so its mass is more. It adds to the weight, and its mechanical strength is also less. We use lead in pencils also, so its mechanical strength is less. That's why some other metals like aluminium is used. Aluminium sheaths are very common and they have good mechanical strength than lead, and also their weight is less. That's why they are also used. They have several applications. Aluminium also used in aircraft. Aluminium alloys are used. Duralumin, and all the others. Several wherever we require lightweight application, aluminium is widely used. So here also, that's why aluminium is used. And then this is the sheath. Then what next comes the armor. So what is the use of armor? Now armor, first of all, so let me insert one new slide, blank slide. So first of all, we had this conductor. Outside this conductor, we have this insulation. Then over the insulation, we have this sheath. Now, over the sheath also we have another covering, which is the armor. So Deepak, can you tell what would be the use of armor? If sheath is to protect insulation from mechanical damage, what will armor do?
It will protect the conductor.
So it will protect just the element which is the layer just below it. So what is the layer just below armor? So this is conductor is innermost. Above conductor is insulation. Then over the insulation we have another coating of sheath. Above sheath we have armor. So armor will protect which layer? Sheath, correct. And sheath is protecting conductor. So in turn armor is protecting conductor also, but the immediate layer is sheath. So armor will protect sheath, and that's why armor is a kind of steel tape, and it is a kind of wire, steel tape or wire armor. And if you have seen, I don't know whether you have seen a cable or not. If you see a cable there, when you remove the outer covering, then you will find there are some cross-linked these wires, or not. They are not thin wires; it's flat kind of wires. So they will be wound around the cable to protect the sheath. It's very common, especially for big high voltage cables. So they will consist of different tapes, steel tapes, and they are coated with compounds. Yes, yes, Deepak.
Sir, in India there is have done the underground distribution system.
Yes. It is there. And especially you will find them in these metro cities. Like in Mumbai, Jaipur, Delhi, you will find underground cables. But in other towns, small towns, you will not find. Mostly there will be overhead lines, distribution lines, or some places they also have these overhead cables. So they are PVC cables or polyethylene cables, which are 11 kV cables. They have even, so mostly you will find entirely underground distribution network is also in campuses. You will find these education institutions or government campuses. These big campuses, just like IIT Bombay is there. So in IIT Bombay, the entire distribution network is mostly underground.
Sir, in cities when we want to take new connection, then how can we do?
No, so what happens? In between, they have one box. So cables are laid underground, but at certain distances, they keep one one box is there. I don't know whether you have seen, but so that what happens? That box will be connecting. It will leave the out inlets or the points where we can connect consumers to that cable, to that distribution network. So at regular distances, there will be such boxes where we can connect. We can make new connections. Otherwise, you are correct. Once a cable is laid down, we will not dig down to make a new connection. That is not a good idea. So once the cable is laid down, such regular, just like in overhead distribution system, we have these poles, right? And at regular intervals, and at poles we draw new connection. Similar to that, all the cables are laid underground, and above the road they have these boxes. So where we can make new connections. Is this fine?
Yes, sir.
Yeah, so we were talking about armor, right? Armor, so it's a tape kind of metal, or it's kind of wire, flat wire, mostly flat wire. So it will be wound around, and then above that we'll be having this covering to protect the entire cable. So armor and everything, it will also prevent. So this is also, it is coated, this armor consisting of these wire tapes is also coated with several kind of preservative compounds to preserve that pattern tape, and that is why it is applied helically. You will have you seen any cable, Deepak? Not
Yes, sir, I have seen.
Which one?
Sir, I think I did not see underground, but where had I seen like cables?
No, have you seen the ones, the inner cross section of cable? Not necessarily these power cables. You could see these even the cables which are used for dish TV, DTH, or some other kind of cables. Even sometimes when they are making connection at your home, if you would have seen cables. So there you will see. You can sometimes, if some new connection, whenever a new connection is made to a new house from existing distribution network, you will find these three-phase cables if are there. So they are very thick, and in that you will find all these things. Most of these things will be there. You will find covering is there, and that covering, it is not entirely, what we say, circular, because the wires are wound in helix. So you can see on covering also, it will be not smooth because wire are wound. So you can see that clearly, it is visible. And when you open it, then first thing is that it's steel tape, which is also wound like a wire, like the conductor. Then you will find this sheath and then conductor. So it's, and in big cables we have all the three conductors within the same. So it will provide a good protection against the mechanical damage, but steel wire armor is recommended where additional longitudinal stresses may occur. So let us move. Then also there are different types of cable based upon, because when the voltage increases, to provide that insulation and also to avoid some kind of voids or any kind of impurities, if there voids are there in the dielectric, then it can create hotspot and dielectric breakdown. So that is why gas filled or oil filled or gas pressurized cables are used. So these are other cables, and these pressurized cable can be used up to very high voltage level. These are very high voltage cables. So they can be used even up to 500 kVs voltage, 500 kilovolts.
Sir, what will be the size of the cable like 500 kV?
Yeah, it will be huge. It will be very thick cable. Even if you see 33 kV cable, mostly you will see if you go to some substation, distribution substation, there you will find 33 kV cable easily. You can see that. It is also very thick, around how much I will say. Have you seen this kind of tape? Have you seen? So you can easily find around this much width of cable in distribution system. Then you can just imagine how thick cable would be required for 275 kV. So that's why these at such high voltage we have these transmission lines. Cable become very costly. It's very costly. So generally we use cable only at distribution levels. Okay. So then, after discussing different types of cable, we went through how to what are the different parameters of a cable? How can we characterize a cable? Just as in transmission line we have R, L, C and G. So here also we have different parameters like resistance, which is insulation resistance we have, and we have capacitance of cable. These are the two main parameters for a cable. So capacitance is quite high in case of cables. This resistance for each conductor, it depends upon many things. So resistive element is generally considered as a loss, right? It creates loss. It's whatever power is being delivered, resistance results in a loss. It results in dissipation of energy. In wire, if we have a wire, a normal wire, then it has a resistance and it will result into I square R loss or heat loss, right? So here also it is this resistance of cable is affected by skin effect, proximity effect. So I think you should remember all these things. This question can also come on what are the different parameters which affect or which determine this resistance. Sheath loss, armor loss, and DC resistance. So normal if we have only DC supply, we have only DC resistance. But when we have the skin effect, we have AC supply. These four other terms also come into picture, and these increase this DC resistance. So overall effective resistance will be in addition to this DC resistance. So Deepak, do you know this skin effect, proximity effect?
Yes, sir. Skin effect, like in case of AC, the current distribution is the around the surface of the conductor.
Yes, that is why its name is skin. Correct. Because skin, if we see our body, then skin is the topmost layer, which is very thin. That is why when AC conductor is there, when a conductor is there and AC supply, AC current is being passed through that conductor, then the current has a tendency to only flow over the surface of the conductor. So that is almost like a skin of that conductor. So that is why skin effect, correct. So proximity effect also, suppose if it's a 3-phase cable, then near one conductor we have 3 conductors in close proximity, and each conductor is carrying current which will create its electric field. Because of electric field in each of them, the electric field in one will affect the electric field in other two also. So it will distort the electric field in conductor. So because of proximity means near or closeness. So because of conductor which are close to that conductor, the electric field of that conductor is also influenced. It is distorted, which results into change in resistance. Effective resistance. That is called proximity effect. Then we have sheath loss. So in sheath also, because of current, so we have conductor and then above that we have sheath. So in between we have air. So it acts like a transformer. Just as in transformer we have eddy current losses and hysteresis loss due to induced EMF. Here also similar kind of losses are there in sheath as well as in armor. So that's why these different types of losses are there. And together they will, and to reduce this to sheath losses, what we do in transmission lines, what we try to do to make the impedances equal in all the phases, because we have mutual inductances between two different phases, but so that will result in different inductances if we do analysis. But to make them same, what we try to do you remember what we do? We use one important principle to ensure that. So, have you heard of transposition, Deepak?
Yes, sir.
Yeah, so similar to transmission line, here also in cables also we do transposition to reduce this effect. So we try to, because eddy current hysteresis, they depend upon the path length. So if we reduce the path length, then we will reduce. So we try to at certain intervals we try to do this transposition of sheath, which is also called cross bonding in case of cable. So okay, this is done. Then we went to insulation resistance. So finally, insulation resistance is given by this rho by 2 pi L, ln R by R, where rho is the resistivity and resistance this is radius of conductor and this is R, capital R. So this T is the thickness of sheath. So T is capital R minus small r. So thickness of sheath. So if we plot this electric field versus this distance from this center. From here we can say from R to R. So electric field is maximum at which point? If we call this point as A and this point as B. So where will be the electric field stress maximum? A or B?
Sir, B.
B is this outer one, A is inner one. So B or A? Conductor is here.
Sir, A.
Yes.
Yes, sir, A.
Correct. So A will be maximum. This is E max, and this is E min. So E max, do you remember the formula for E max? If the voltage of conductor is 0, so this is sheath is always grounded. So this is at 0 potential. Conductor is at potential V. So it is given by V divided by R ln R by R, and E minimum will be given by capital R. Correct? So now this is E max and this is E min here. Now what happens, because from point A, E, electric field stress is maximum, here it is minimum. So this stress is non-uniform across the sheath, and because of this it results in this E max and E min, the difference between them is also very high, because we are using only same material throughout. If you want to reduce this E max minus E min, or you want to minimize or make this stress uniform from R to capital R, then there are two methods. Two methods can be used. What are those two methods? So one is called, these are called capacitance grading. methods. Because of this electric field between this conductor and the sheath, and this is the sheath has a dielectric constant, so it results in a capacitance between this conductor and sheath, and this the value of capacitance is given by, what is the value? So because of electric field we have a capacitance between the conductor and the sheath. So if we somehow, because this capacitance is dependent upon this distance between this sheath, and this is resulting in this kind of electric field, but we want this to be uniform or close to uniform. At least we want to minimize this difference. So what we do, there are two methods. One is capacitance grading and another is intersheath grading. So capacitance grading is, we have different grades of capacitances. That means right now we have only single capacitance because of single dielectric element. And entire sheath is made up of only one type of material. So we have only one kind of dielectric constant. But if we somehow divide this sheath and use different types of dielectric materials, then it is called capacitance grading. And by using that we can do something like this. So in all the, let us say this entire difference, this was R and this was capital R, and in between I have made 2. So we are using 3 different dielectric materials with constants epsilon 1, epsilon 2 and epsilon 3. So we will have 3 different electric fields, but we want this Emax and Emin. The ratio of Emax and Emin to be same in all the 3 regions. So here you have written Emax is this, Emin is this. So Emax is V by R ln R by R, and Emin is V by capital R ln R by R. If you take the ratio Emax, what will be this ratio? How much? This will be R by R, right? Fine. So here from this what we can say, that for a given value of voltage and capital R, there is a certain value of R for which we can get minimum value of Emax. So that is why we call this relation of capital R and small r for the optimal operation, for optimal cable sizing. So if we want to minimize Emax is given by this expression V by R ln R by R. So if I want to minimize this value, what should I do? Because V is constant, small r is variable, capital R is also constant here for given V and capital R. So if I want to minimize this Emax, what should I do, people? This is also constant. I will have to maximize this, right? So I should maximize R ln R by R. So for maximizing, what we can do, we can differentiate this with respect to small r. And then finally we reach this relation R is 2.718 R for optimal operation, for optimal design of cable. Okay. Is this fine? Yes? Deepu?
Yes, sir, it is fine.
Yeah, so for capacitance gating, we want to make this electric field same, right? So this 2 pi epsilon r R1. So this was our sheath, this is our conductor, then R1 and R2. So this is R1, R2, and this is capital R. So for each region you can find E as, for this is for first one, this is for second one, and this is for last one. So this will be at x is equals to capital R, that means this, and at x is equals to small r2, this is r1. So this is like this, r1, r2, and capital R. So at r1, r2, and r, this is at x is equals to r1, x is equals to r2. So we want these values to be same. If we want this value to be same, then we have to equate them. Then it will result into, this is r1, this is r2, and this is r3. So epsilon r1 into epsilon r1 into r is equals to epsilon r2 into r1. Did I make a mistake? At r is this, r1, r2, and capital R, r3. Yes, correct. So epsilon r1 into r is equals to epsilon r2 into r1 is equals to epsilon r3 into r2, which is also equals to epsilon r3 into capital R. Because at x is equals to r2 also, this is cube by 2 pi epsilon naught epsilon r2, epsilon 3 r2. For capacitance grading, we will get this expression, and then we can easily find voltage equals to integrate E for each region, E1, E2 plus E3. That way we can do for this capacitance grading. Add one more page, and then next one is the intersheath grading. So although we are using these showing these two methods are not practical because for capacitance grading we need epsilon 1 epsilon. Suppose we are dividing into 3 regions, then we need 3 values of dielectric constant, and then we should have these materials also. Even if we find these values, but if we don't have a material with the same value of dielectric constant, then our purpose will not be solved. Sorry. So we might have slightly different values. So that will also change our distribution. Moreover, with time this dielectric strength also changes. So with time, for the same voltage for which it was designed, that dielectric may not be a good option because it may lead to breakdown with time, because it also has aging effect. So these dielectric values also change with time, temperature and other factors. So that's why this capacitance grading is also not practical. And second, this intersheath grading is also very difficult to apply in practice, because here also if we are making these 3 regions, then we are saying that with capacitance grading it was at voltage V and this was at 0. Now we are saying that we want to change this voltage level itself. We want to maintain these different sheaths at different voltage level. Let's say this is V1 and this we want to keep at V2. So now we will maintain this sheath at a voltage V1, this sheath at voltage V2. For this also it will be very difficult because we have to insert tappings, take tappings from transformer, and to maintain this sheath at that particular voltage. Now we want to cut a cable and join in with some other section. Then this joint is also very difficult to maintain because we want to maintain that voltage throughout. It is also very difficult from construction point of view. That is why this method is also very difficult to do in practice. So here what we will find, if we do not use intersheath grading, then we will find electric field distribution like this. Variation of electric field will be something like this. But by using intersheath, because we want to minimize this difference Emax and Emin, so we are able to achieve that. We get this as Emax and this as Emin, and so we have these different values. This was R, this was capital R, and in between we had R1 and R2. Say this is R1 and this is R2. So here we will get something like this, electric field like this. So we are getting like this. This single curve is without intersheath and this is with intersheath. So whenever there is change in we move to different sheath, it starts from Emax, same Emax, and reaches at same Emin at the end of that sheath. And then at the starting of the another sheath, it will start at Emax and again reach the same Emin. So here also we are trying to maintain this ratio. So we want this Emax 1, Emax 2, Emax 3 equal, same. Similarly, we can also equate Emin. We'll get same equation. Different equation, but because we have different R, but we will get same value. Final answer will be same. Either we equate Emax or equate Emin. So here we can write Emax 1 as V minus. So E is V divided by R ln R. So here V will be this V. Here the voltage is V, potential. Here it is V1. So difference will be V minus V1. It will be V minus V1 divided by R ln R1 by R. Because this is R because we are writing for Emax. Maximum value will be at this R. Similarly, for this intersheath, maximum value will be at R1, and for third one it will be at R2. And this is R1 by R because it ends at R1. Its thickness is, this is R, this is R1, then this is R2, and the entire this is capital R. So Emax 2. So can you tell Deepak what will be Emax 2? Just as we write Emax 1. Can you tell what will be Emax 2? Just see the voltage difference, the radius which we want to use. Are you there, Deepak?
Yes, sir. Sir, it will be V1 minus V2
Yes. Divided
by R1
R1.
ln R2 by R1.
Yes, correct. Good. Similarly, we can write for Emax 3 also. So it will be V2 minus 0, so it is V2 only. It will be R2 ln capital R by R2. Now we want to equate them. And also, if we want this, because we want the ratio of Emax and Emin to be same in all the intersheath, and this we already know that this equation is equals to the radius at minimum Emax divided by radius at maximum. So this will be, if we say Emax 1 by Emax min, it will be minimum is at R1 and maximum at R, because for this intersheath, for this region, this is minimum Emin at R1 and maximum Emax is at R. So this is R1 by R. Similarly, for this is also Emax 2 and minimum is here. E minimum 2. This is, so ratio will be, for second it will be R2 by R1. So you can write R1 by R is equals to R2 by R1 is equals to R by R2. And this we can, this ratio we want to be same. So we can say it is alpha. And if you multiply these three, then this will cancel. Right? It will be capital R by small r into, because each one is alpha, multiplication will be alpha cube. So we can write, and because from these three equations we can equate them, and we can write V minus V1 as R ln alpha, V1 minus V2 as R ln R1 ln alpha, and V2 by R2 ln alpha. So this we will use in numerical. Now we will see numericals also. There we will use this thing. That is why. So as I was telling, the disadvantages of these two methods is that if we, same thing, we need different materials with all these possible values, and also their permittivity changes with time. So with intersheath grading, it is difficult to arrange for proper voltages of intersheath. That is also a problem. So if we calculate the voltages, we need those two particular voltages for intersheath, and then joining cables having intersheath also causes problems. So now we will see numericals, right? We will take problems. Let us start with this problem. This is first. Initial first two problems are MCQs. So first one is the voltage stress in underground cable is. So which option is correct? Maximum at conductor surface and minimum at sheath, or minimum at conductor surface and maximum at sheath. We just saw this, right? So what is the answer? Is it same at both conductor and sheath, or is it 0 at conductor and sheath? Which one is?
Option A is correct.
Yes, correct. So we saw that if we have conductor here, and this is our sheath. So this is radius, sorry. This is R, small r, and this is capital R. So we have the electric field distribution is something like this. Maximum at conductor and then it is minimum in the sheath. Because we know the skin effect is there. In conductor, most of the current will be at the surface of this conductor. So electric field will naturally be maximum at this because we potential gradient also it will reduce. It will be maximum at this surface. After that it is dielectric. Gradually it will reduce. With distance electric field reduces. Source of electric field is here at the conductor surface. Now let me just connect charger to a laptop. Yes. So next question is this: the purpose of using sheath in cables is this also we discussed. We had discussed this. So the purpose is to first one is to provide strength to the conductor, to provide insulation, to prevent moisture from entering in the cable, and or to reduce the capacitance. So this is already done by insulation. The covering over the conductor is the insulating material which provides the insulation. Then above that insulation we have sheath to prevent moisture from entering the cable, right? So this is the function of sheath. And above sheath we have which one? Which coating? Deepak, do you remember?
Armoring.
Yes. So above this will be having armor. And above armor will be having last covering. The last covering of the cable. So this will also protect this armor. This will protect the sheath, and sheath will protect insulation. Insulation will protect all conductors from it will provide insulation between two different conductors and whether conductor and from other kind of conducting materials. Right. And now we'll move to the numericals. So first question is a single core cable 2.5 km long has an insulation resistance of 400 mega ohms. If the conductor diameter is 4 cm and insulation thickness is 3 cm, calculate the resistivity of dielectric in the cable in ohms meter. So which formula are we going to use here? So we know the length of the cable, we know the insulation resistance.
R is equal to
rho L by A. Yes, this is for if we have a simple wire, but here we have a cable, and for cable we have, because we have conductor here and we also have a sheath, and we are here talking about the insulation resistance. Oh, sorry, this is insulation, not sheath. Sorry. So we are talking about insulation resistance, not the conductor resistance here. So we want this resistance of this material. So it will not be simply rho L by A because it is varying, right? Its thickness is varying, and with thickness the resistance is also changing because it's a area. So let's say we calculate it. We have to do integration. If we have this conductor at radius r and insulation at r, capital R, and take a small element of length dx and then integrate the dx from r to capital R. That is why we saw this formula of rho upon 2 pi L ln r by r. Right? We saw this formula. Right? We discussed this. So instead of this, we will use this. So now here we know this R is capital R is this, and 400 mega ohms. Resistivity we have to find. We have 2 pi. Length we know 2.5 kilometers. So we will multiply it, convert it into meters. So this is in, because this resistivity is in ohm meter. So we have to divide it by meter to convert into ohms, because this R by R is dimensionless. So what is capital R here? Can you tell people what is smaller than capital R here? So you have to see, this is diameter, not radius.
The capital R is 7 centimeter and small r is 4 centimeter.
That's what I'm saying. This is diameter, and here we are talking about radius.
Yes, sir. It is 5 centimeter capital R.
Yes, correct. So please, whenever you, while you are giving your test also, while you are taking your test online for NPTEL exams, then also you always check, read the question carefully. So this is diameter. So first, either you take diameter for both of them, or you take radius for both of them. Don't mix. If you take diameter of one and radius of other, then it will be a problem. Because suppose if you take diameter, right, so it will be ln capital D by small d. In this case, d is 4 centimeter, and so capital D will be 10 centimeters, because you have to add thickness on both the sides. Right? So this is diameter d, which is 4, and thickness this is 3, but this is also, this side also it is 3. So total it will be 10. So now if you take ratio of 10 divided by 4, then it will be 5 by 2, 2.5. Here also, if you take radius, then radius is 2 centimeter plus thickness is 3, so radius becomes, capital R becomes 5. Here also ratio is 5 by 2. So you can take diameter or radius, but both should be either diameter or both should be radius. But we cannot mix, otherwise it will result in error. So this is the final. Now we just have to multiply. So can you calculate, Deepak, what will be the value? So resistivity will be simply this 400 into 10 is power 6 into 2 pi into 2.5 divided by ln 2.5. How much is this value? Are you calculating? You can use calculator.
Yes, sir.
So it will help you if you do calculation here. You will get practice and then you will not make mistakes in exam. So you can do calculate and just tell me what is the answer.
Sir, my answer is coming 6.857 into 10 to the power 12.
Yes, very good, very good. This is correct. 6.857 into 10 to the power. So plus 12 ohm meter. Always keep right units also. So this is correct. 6.85 is correct. Now let us move to the next question. So next question is, for a three-phase transmission system of voltage 765 having a core radius, so radius is given, so you have to see this is a radius 5 centimeter, and outer radius, this is also radius, this is 0.4 meter or 40 centimeters. So you were asking it how big the cable will be required. You can see here inner conductor radius is 5 centimeter and the outer radius is 40 centimeters. It's very huge. And for 765 volts, this much which will be the width of the cable. This is radius, so diameter would be 80 centimeters, around almost 1 meter. 1 meter is very huge. So it will be quite huge cable. As the voltage increases, this thickness of cable also would increase. That is why the insulation becomes a problem. Providing insulation at 765 kV, it's and too for underground cables, it's very difficult to design such an insulation. It will add too much to the cost also. Yeah, so here we want to calculate the maximum dielectric stress on single core cable. So voltage is given, everything is given, we want to calculate the stress. How are we going to do this? Which formula we'll use? We discussed this formula also. Which one? Do you remember?
Right for it.
No problem. We'll do this. So you have to remember only 2-3 formulas in this. So one you can remember, one is for insulation resistance. So that is rho 2 pi L by 2 pi rho by 2 pi L into ln R by R. This is insulation resistance. Then you have capacitance 2 pi epsilon naught epsilon R by ln capital R by small r. This will be in farad per meter, and this will be in ohms, because this is in ohm meter and we are dividing by length, so it will come out to it will be in ohms. Then next formula you will find E for E is V by R ln R by R. This is E max, or you can write it as Ex V x ln R by R. So this is another formula. Then for capacitance grading you have to remember E1 R is equals to E2 R1 equals to E3 R2. We'll see. Let us do questions, and while practicing you will also remember. Only 4-5 formulas are there. We will not remember much formulas. So here it is asking for maximum electric stress. So let us first see what is the radius. So inner radius, conductor radius is small r is 5 centimeter. Already radius is given, diameter is not given, so it's good. Then outer radius is given, outer radius is capital R, which is 0.4 meters. That means 40 centimeters. So now we have to find E max, maximum dielectric stress. This will be V divided by maximum is it smaller, because we know that it is maximum at the conductor radius and minimum at the outer radius. So it will be ln capital R by small r. Now one thing which we have to remember is this voltage is, this is per phase for each core. So in 3-phase cable we will be having 3 cores. 3, and it is 1 cable. So this voltage has to be phase voltage. Whenever 3-phase system is given and nothing is mentioned, it is always a 3-phase line to line voltage. So this we want to be phase voltage, so we will divide it by root 3. Then small r is how much? 5. ln capital R is 40 centimeter divided by 5. So calculate, Deepak, how much is this? How much are you getting? So here everything is in meter, right? So we have to convert this into meters. 5 centimeters. So multiply it by 10 to the minus 2. This will be in meter. Now whatever you will be getting is, it will be in volts per meter. 6 kV, kilovolts, because this is also in kilovolts. 765. So how much is this value?
So it is 42.47 into 10 to the power 12.
42.47
into 10 to the power 12.
Why 10 to the power 12? So this is 10 to the power minus 2.
Okay, minus 2, then it will be minus 2. No, it will be 2.
Yes, correct. So because this, do you know why this 10 to the power minus 2 is coming?
So we want to convert it centimeter to meter.
Yes, 5 centimeter is 10 to the 5 into 10 to the power minus 2 meter. That is why we have used it. So this is correct. 4 to 4, it will be, if you round it off, it will be 4248 kilovolt per meter, because 765 is also in kilovolts and this is per meter. If this is in centimeter, we will get it in centimeter. We have converted it into meter. So answer C is correct. Good. So this was easy. Let us move to the next question. Now this one, yes, this is another question. Same formula we are going to use here also. So what is the question? Question is, the maximum and minimum stresses in a dielectric of a single core cable, are 40 kV per centimeter in RMS and 10 kilovolt per centimeter in RMS. If the conductor diameter is 2 centimeter, find the thickness of the insulation and the operating voltage. So this is the question. So what are we going to do here? It's a single core cable. We have this R and capital R, small r, capital R. We know the formula for Emax. Emax is how much? V divided by R ln capital R by small r. And Emin is how much? V by capital R. Now what we can do here, take the ratio Emax divided by Emin. How much is this? This will be capital R by small r. And Emax by Emin, we know the values of Emax and Emin. Emax is 40 and Emin is 10. So capital R by small r is 4. And we know the conductor diameter. So this is diameter. So radius will be, small r will be how much?
Centimeters.
How much?
Sir, 1 1 centimeter.
Yes, correct. So R is 1 centimeter. So capital R will be 4 centimeters. So what will be thickness? So this is 1 centimeter.
3 centimeter.
Yes, correct. So thickness is capital R minus small r, which is 3 centimeter. This is correct. Now we have to find the voltage. So you can use any of these expressions. So let us say use this one. Find voltage. E max we know. E max into R. So calculate this. Deepak, what is this value? So this we know is 40 kilowatt per centimeter into, because it is in per centimeter, so it can directly use radius in per centimeter. This is 1 ln 4. How much is this? Calculate. Yes. So it is 55.45 kV. So this is also done. So thickness is 3 centimeters and voltage is 55.45. So easy, right? Easy questions. Direct formula based. This is also done. Good. Now let's move to the next question. This is a single core cable working in 45 kV on 3 phase as a conductor diameter. It is diameter 2 centimeter. So radius, let us write radius first. 1 centimeter is the radius. And inside diameter, this is also diameter of sheath radius. That means capital R is given as 5 centimeters. It is desired to reduce the maximum stress by using 2 intersheaths. So it is using intersheaths, and 2 intersheaths are being used. So this is conductor radius R, 1 intersheath, second intersheath, and then we have outer radius capital R. So this is R1, then this is at R2, and this is capital R. So we'll find R1, R2, both this we have to find. We also have to find the voltage. Determine the peak voltage on the second intersheath V2. This we have to find. Peak voltage we have to find. So let us see how to do this. So whenever this is given 3 phase, nothing is mentioned. Which voltage is this? Deepak, which voltage is this? 45 kV?
Line to line RMS.
Correct, line to line RMS. So we have, everything is being asked in peak. So how can we convert this line to line RMS into peak? Per phase peak.
So just multiply by √2.
And also this is phase voltage, right? For each phase we will be having this. So
And divide by √3.
yes, correct. So it will be, peak voltage will be 45 divided by √3 multiplied by √2. This will be peak voltage. So this is V. So this conductor voltage V. We know. V is given. So this intersheath is at V1, this is at V2, and final this is at 0 potential. So we want to calculate V2. We will also calculate V1 in the process. So let us start. Now because we have this intersheath, what we wanted to do, we saw, right, how this functions. What is the function of, why do we add intersheath? We want to maintain the ratio of Emax by Emin same in all the 3 regions, right? This we want to maintain, because this is, here it is Emax, so we want this kind of profile. So we want these 3 values same, these 3 values also same, so ratio will be same. And this is R, this is R1, this is R2, and this is R. So Emax by Emin is R1 by R, which is also equals to R2 by R1, which is equals to capital R by small r2 and this is equals to, let's say, alpha. And if you multiply these three, we get r by r as alpha cube. Capital R is known, small r is known. How much is this? Capital R is 5, small r is 1. So, Deepak, what is the value of alpha? Calculate. How much is this? This is cube root of 5. How much is this?
Sir, 1.7.
Yes, 1.71, correct. So now we have another equation. This ratio is same and also Emax is same in all the three regions. So now we have to write equation for Emax 1, Emax 2 and equate them, and Emax 3, and we already did that. So it will be V minus V1 divided by Emax is maximum is at R, ln R1 by R. Here Emax is, it is V1 minus V2, maximum is at R1, ln R2 by R1, and this is V2 minus 0, so 0, ln capital R by small r. But we know that R1 by R, R2 by R1 and R by R2, so this is R2. It is alpha, so we can write this as V1 minus V by R ln alpha. This as V1 minus V2 by R ln alpha R1, and this is V2 by R2 ln alpha, correct? So here we know V, we don't know V1 and V2. So what we can write, we have these three equations. We can solve for, let us find out expression for voltages here, V1 and V2 in terms of V. So again, let me just copy this. Okay. So we have this equation. What we can do, let us write. So now, because ln alpha is common, so we can cancel it. We are getting sorry, V1 sorry. So we have this V minus V1 by R and V1 minus V2 by R1. This is V2 by R2. One equation we can write here as V is equals to R times V1 by R plus V2 by R2, right? So which is V1 plus R by R2 into V2. Let me also copy this. This will be also required. This relationship also. Why am I not able to copy? What is happening? Okay, let me write it again. Yes. R by R1 is equals to, sorry, wrong. R1 by R is equals to R2 by R1 is equals to R by R2 is equals to alpha, right? So now what we can do, this is R by R2. If we want to get this capital R by R2, what we can do, if I want to convert this R by R2 into capital R by R2, can I do this? What can be done to do this? And we also know that capital R by small r is alpha cube. Yes. Can you tell, Deepak? How can this be done? I want to convert R by R2 into capital R by R2. Because I know I know this capital R by R2. I don't know what is the ratio of R by small r by small r2. So I want to calculate this. So what can be done to do that? Any idea?
Sir, I think we can write it in form of R, like R1 minus the distance between them is R.
So that will again subtraction and all that will come. What you can do? Simple thing I can tell you. What you can do, because we want capital R, right, in the numerator, but we don't have capital R, so multiply capital R in numerator and divide by same. So what you will get? Capital R by small r, right? Now you know this. What is this? Capital R by small r? 2. This is alpha, and this also we know. Small r by capital R is 1 by alpha cube. Correct? So r by small r2 will be alpha by alpha cube, that means it is alpha square. Correct?
Yes, sir.
Yes. So this is 1 by alpha square v2. Now we want this only in terms of either v1 or v2. We need one more equation which relate v1 and v2. So let us write this: v1 minus v2 by r1 is equals to v2 by r2. From here we can write v1 in terms of v2. So v1 by r1 is equals to v2 by r1 plus v2 by r2, right? And v1 is equals to v2 plus r1 by r2 into v2, and this r1 by r2 is 1 by alpha, so v2 is 1 plus 1 by alpha. So this we can substitute here. So this is v1 plus v1 we have to substitute as v2. So v2 into 1 plus 1 by alpha plus v2 by alpha square. This is v. So this is 1 plus 1 by alpha plus 1 by alpha square v2. Yes. So can you see, Deepak, this is like it's a GP, right? Geometric progression. So you can even generalize this. What we have here is, we have a conductor, then intersheath 1, intersheath 2. Suppose we have intersheath n, and then we have capital R. Then we can generalize this for V2. For Vn it will be 1 plus alpha, 1 plus 1 by alpha plus 1 plus 1 by alpha square up to so on up to 1 plus alpha raised power n. So we can do that. So this we can generalize. If we have only one intersheath, then it will be only 1 plus 1 by alpha. V1. So in lecture it was done only for one intersheath. So here we have did it for 2. Now we can generalize it. If we have third one, then it will become 1 plus. So first voltage, this conductor voltage V will be related to, let's say this is V1, this is V2, this is V3, and this is 0. So V3 will be V. So V will be 1 plus 1 by alpha plus 1 by alpha square plus 1 by alpha cube into V3. This will be the relation. So is this fine, Deepak? Is this understood? So this is a very interesting relation, right? It's a geometric progression. So if you want to relate V2 with V3, then it will be 1 plus 1 by alpha plus 1 by alpha square. Just like we can see here, V1 is 1 plus 1 by alpha V2. If we have one more, then it will be V1 is equals to 1 plus 1 by alpha plus 1 by alpha square V3. And V will be one more term, plus 1 by alpha cube. Is this fine? So one thing which we wanted to calculate was value of V2. V2 will be V, which we know, V divided by 1 plus 1 by alpha plus 1 by alpha square. So can you calculate, Deepak, what is this value of V2? First calculate this 1 plus 1 by alpha plus 1 by alpha square, and then divide V by this value. So what is this value? Calculate. How much are you getting?
Value of alpha.
Alpha we calculated cube root of 5, 1.71. So alpha is cube root of 5 because r by r. This is 5. So this will be cube root of 1 cube root of 5, 1.71. So calculate this value of V2.
What is V1?
V is for this. V is this 45 root 2 divided by root 3.
So I am getting 19.06.
I think it's correct. Let me check. 1926. It should be correct, I think. This V2 is yes, correct. 19.06. That is correct. So yes, now we have found. Now calculate V1 also. V1 is this V2 into 1 plus 1 by alpha. How much is V2? Sorry, V1. V2 is correct, 19.06 K. So now from this V2 you can calculate V1 also. Multiply it by 1 plus 1 by alpha. How much is V1? How much are you getting?
19.32.
No. No. This is 19.06 multiplied by 1 plus 1 by alpha. V2 into 1 plus 1 by alpha. It will not be this much. 1 plus 1 divided by 1.7.
No, sir, it is 30.20.
Yes, correct. So alpha here is 1.71, right? So how much? 30, yes, 30.2, that is correct. 30.20, correct. So this is correct. Now we have calculated V1 and V2. Now also let us calculate R1 and R2. So we know this alpha is 1.71, right? So R1 is R into alpha. R is, how much is R? R is I think 1 centimeter, right? Yes, R is 1 centimeter. So this is same as 1.71 centimeter. Calculate R2. R2 will be alpha into R1. How much is R2? Calculate R2. Oh, 2.9, right? Yes, 2.92 centimeter. So now this is done. R1 we have calculated, R2 we have calculated V1 as well as V2. Now let us move to the next question. So this is done. Next question, so this is correct. Yes, next question is same question, it's continuation of that. What is the ratio of maximum stress without and with intersheath? So where we were here, right? Here. Now we have calculated this. Let me insert one more page here, one more slide. So we have calculated this V as V as, or let's say V2 as V divided by 1 plus 1 by alpha plus 1 by alpha square. This is our V2. So this is with intersheath, and we know that Emax 1 is equals to Emax 2 is equals to Emax 3, and Emax 3 is equals to V2 divided by R2 ln capital R by small r2, right? And V2 is this, so we can substitute it here. It will be V divided by 1 plus 1 by alpha plus 1 by alpha square into R2 ln alpha. No, sorry. R by R2 is not alpha. Let us again use that. R by, sorry, R1 by R. This expression is very important. We will require it again and again. Capital R by R2 is alpha. And we want R by R2. This is alpha. So this is alpha. This is same. Alpha. Now we want to replace this R2 also. We don't want R2. We want it in terms of known quantities. Known quantity, let is only R, capital R, small r and alpha only. So how we can change this? We can write this. Use this. We can write R2 as R by alpha. So it will be V alpha into 1 plus 1 by alpha plus 1 by alpha square capital R ln alpha. Now it is in terms of capital R and alpha. Now this is with intersheath. If we write it without intersheath, so without intersheath, the Emax will be V divided by, because now we have only this R and this is capital R, and this is at V, this is at 0, and maximum electric field stress will be at small r. So it will be, yes, small r into ln R by R, and this we already know. R by R, how much is this? Capital R by small r is how much?
7.7.
In terms of alpha, how much?
The alpha cube.
Yes, correct. Alpha cube. So this we can write as V3 R ln alpha square. Now we want the ratio of these two. Ratio of without intersheath. So first tell me one thing. Which one will be higher? This Emax, let's say bar, and this Emax. Which one will be higher out of these two? With, it will be more with intersheath or without intersheath?
So without.
Yes, correct. So we have to take ratio of this second with the first. Second divided by first. So without intersheath divided by with intersheath. So it will be V divided by 3R ln alpha square. So here it will be V alpha into 1 plus 1 by alpha plus 1 by alpha square into R ln alpha. So here V will cancel out, ln, sorry, this is alpha only. Why am I writing alpha square? This will cancel out. So here we are getting how much? This is R, and R by small r we already know, this is alpha cube, and there is one alpha here. So it will be alpha square by 3 into 1 plus 1 by alpha plus 1 by alpha square. So we can further simplify it as, because if we take this, if we take LCM, it will be alpha square, right? So it will be alpha square plus alpha plus 1 divided by 3. Is this fine, Deepak? Is this correct?
Yes, sir.
So now we can see this ratio is independent of voltage. It is purely dependent on alpha, and alpha is the ratio of R by capital R by small r. Correct? So it is simply dependent upon alpha. So please calculate this value. So this is, as you said, it should be more than 1, because it is 1 plus something, and alpha is always positive. Alpha is always positive, so it will be always greater than 1. So how much is this ratio? Calculate.
1.878.
Yes, correct. 1.87. Good. So this was the next question. This was the question. Find out the ratio of maximum stress without and with intersheath. So that we have calculated in terms of expression also. First we calculated the expression, which is alpha square plus alpha plus 1 divided by 3. And this ratio is, after substituting the value, we get 1.878. Let us move to the next question. This is done. Yeah, next question is a single core cable employing 3 layers of insulation. Now this is for that capacitance grading. Last example was on intersheath grading. This is on capacitance grading.
Here I was one question.
Yes, tell me, ask.
Sir, if we don't use these two ratings, then what we use generally?
Then we use the same Emax only, simple single core only here, and this. So this will be small r, this will be capital R. But what we do, we use this oil-filled cables. So if there is any void or something, to avoid that, if there is void, then electric field stress will be more at that void, and that can result in breakdown. So to avoid that, we use this oil-filled or gas pressurized cables. Because in practice, this capacitance grading and intersheath grading are not feasible. Practically, it's very difficult to implement them. So we are using these oil-filled cables for high voltage cables. Okay.
Yes, sir.
Yeah. So here, this one is capacitance grading. Now this is also creating 3. It is creating 3 regions with 3 different dielectric constants. So first one is 5, 3.5 and 2.0. So here also we want that maximum to be Emax 1, Emax 2, Emax 3 should be same. So finally when we do that, we come out with this E1 into ER1 into R is equals to ER2 into R1 is equals to ER3 into R2. So what is the question here? Conductor radius of 1.5. Let us write first this. R is 1.5 centimeter radius. Assuming that all the 3 insulating materials are worked at same maximum potential gradient. So from equating that we get this relation. Same maximum potential gradient. Determine the safe working voltage in RMS. And this is given in kV per centimeter. So this is in peak. It is given peak. This is peak. So we have to calculate it in RMS. So we'll divide by final answer. We will divide it by root 2. Correct. So yes, we have to find out the safe working voltage. This voltage we want to find out. This voltage. So voltage, this will be equals to Emax that we know. it will be common, and it will be E max into how much? Because we write E as V divided by R ln R by R, right? Now we are calculating V, so we just multiply it with this. So E max into it will be R into ln R by R, sorry, R1 plus ln R2 by R1 into R1 plus R2 ln capital R by small r2. Yes, so can you calculate this value? You can write this, right? R1 by R. So from here, from this equation, here R1 by R is equals to how much? Epsilon 1 by epsilon 2. So it is 5 by 3.5. Similarly, R2 by R1 is 3.5 divided by 2. So 1.75. And capital R by small r2 is how much is capital R? Inner radius is sheath is 5. This is capital R is 5. 5 divided by R2 is how much?
3.5.
No, R2 is not 3.5.
Sir, they only give a radius of conductor.
These are dielectric constants. So from here you can find out. R2 you can find out here. So R1 will be how much? Calculate this. R is 1.5. So 1.5 into this. How much is R1? Calculate first R1. So multiply this R into this 5 divided by 3.5. How much is R1? Calculate. So first of all we have to calculate R1, R2, R3. So calculate R1 first.
Sir, R1 is 2.14.
R1 is 2. Just a minute. 2.14. Okay. Now calculate R2. Multiply this with this 1.75. R2 will be
75.
how much? 3.3.
3.75.
Yes, correct. So now divide. This will be 3.75. Now you can substitute this R1 by R here, R2 by R1 and R by R2. So and now calculate this. How much you are getting? This is 45. This small r is 1.5 ln 5 by 3.5 plus R1 you have calculated as 2.14 ln R2 by R1 is 1.75 plus R2 just now we calculated 3.75 ln 5 by 3.75. So how much is this? Calculate this value. So this way we will get in peak value. So RMS will be this V divided by root 2. Yes, Deepak, are you calculating?
Yes, sir.
How much? Still calculating?
Sir, 126.17 is a RMS, no, peak.
Yes,
And
correct.
RMS will be divided by root 2. It will be 89.21.
Good. RMS. So 126, 89.5. Okay, correct. So it will be option B. So we have So here this answer is also given peak, but here because the voltage is asked in RMS, so always be careful when you are answering the question. You will get both the options. So you have both the options here for peak also for RMS, but you have to select the RMS one. So be careful. So one mistake which you make is diameter and radius. Then this peak and RMS. So always be careful about all these things. Okay. Now let us move to the next one. Yeah. Next is this. Yes, this. Capacitance of a 3-core belted core cable are measured and found to be as. So this belted core cable is like this. So we have 3 conductors like this, and then this is sheath. So in between sheath and conductor we have a capacitance called sheath capacitance, and in between these two conductors, let's say this is A, B and C phase. In this between these also we have this capacitance C cable capacitance, let's say. So these are 3 capacitances C, and this is sheath capacitance CS. This is also sheath capacitance CS. Now this is delta. We can convert this delta into star, right? How can we convert? What will be the conversion if we convert this delta connected cable capacitance into star? What will be the value? This is CS, this is CS, this is CS. How much will be this? Deepak, do you know how to do conversion star delta?
Sir, I know, but sir, I generally confused in this. In star to delta, I think numerator will be same.
Numerator will be same, and so what will be the value? So what happens when we have this like any, let's say this is some x c x c x c. Now we want to convert it into star. This is x naught, right? So x naught will be this product of these two, xc into xc divided by sum of all the 3. So here it is 3 times xc into, so it is xc by 3 only. So 1 by omega c naught is equals to 1 by 3 omega cc. So how much is c naught is 3 cc. Is this clear?
Yes, sir.
If you want to move from here star to delta you want to do, then it will change. Then you have to write, suppose you want to calculate this, right, this one. Then you have to take this product of these two. So then I have to change it, nomenclature, A, B and C, something like that. And suppose you want to calculate AB, then AB will be XA XB divided by XA XB plus XB XC plus XC XA. Okay, now we are doing what? Now finally we are here. So here. This is final. So we get 3C. This is 3CC, 3CC and CS. So now this is neutral, and now we want to find this is center of core and this is our ground. Neutral, you can say. Now we want to find the capacitance this between this. So how much will be this? It is how much? It is parallel combination. So capacitance between these two points is 3 cc plus cs. Right? So capacitance of core to neutral. So this is core to neutral. It will be this one. But we cannot directly measure these. So we use these. We make two other measurements. So first measurement is this. So between three cores bunched together and the sheath. So what we are saying, this 3 core. These are the 3 cores. So we are short circuiting them, and this is already 0. Already at the same potential, which is grounded neutral 0. So now these 3 points are same. This is ABC are at same. This A, B, and C here, and this is sheath. So between A and sheath is CS. Between B and sheath is also CS. And between C and sheath is also CS. And we want to find out capacitance between these two points. So how much will be this? Capacitances are in parallel. So what will be this?
So CS plus CS plus
Yes. So
3 CS.
3 CS.
3
Correct.
CS.
So it is 3 CS. Let us call it a CB is 3 CS. So it is given it is 3 CS is given as 12 microfarad. So how much is CS? It is 4 microfarad, right? So now we know CS is known. CS is 4 microfarads. Now we want to find out CC. So for that another measurement is done, which is part 2, which is this one. Between conductor and the other two connected together to the sheath. So between one conductor and the other two connected together. So two conductor, these two are connected together. And now we want between this point, this and the sheath. So how are we going to do this? So this is, let's say, this is short, this is CS, this is also CS. This is CC and this is CS. Did I miss something? Yes, one more. This. No, it is something like this. We want, let's say this point is point capital A and this is capital B. This is also capital B, this is also capital B. Now, so how to do this? This is CC. How to do this? So these 2 points are same potential.
But these two are in parallel CC.
Yes, so CC and CS. These CS are in parallel, right?
So CC as well have both the point is common.
Which one? This one and this one.
CC and CS both are parallel.
Yes. One is this point, one is this point, A to B. these two are in parallel, right? CS.
Yes, sir. CS and these two CC will also in parallel.
Yes. So these two are in parallel. These two are also in parallel. So if two are in parallel, so this is 2 CC, right? And 2 CS. Correct?
Yes, sir.
Now what will happen?
Now it will be in parallel, like parallel combination.
So the one is this CS, another is
And another is
oh sorry, there is some problem, right? So these two are already connected to each other. I think I have made some mistake between one conductor and the sheath, okay, and the other two connected together to the sheath. Yeah, sorry. So these two are connected together and connected together to the sheath. They are connected together to the sheath. So that is the mistake. So fine, it will be like this. So this is conductor A. Suppose this is point A, this is point B. So in between we have CS. Here it will be CC and here it will be again CS. Oh, sorry, CC. Is this correct now? Because these two are connected together and they are connected to the sheath. So all these 2 point and this sheath, they are at same potential. So now this will also go. This will also not be there. CS will not be there. So these two are connected together to the sheath. So sheath is here. It is like this. It is like this. Connected together to the sheath. Is this correct? Yes, Deepak?
yes, sir.
Yeah, so finally we will get this. We will get this. CS and 2 CC in parallel. These two CC and the CS. These two are again connected to the same potential. This is B, sheath only. This is also B, sheath. This is A. So this is also connected to sheath, this is also connected to sheath, and this is sheath here. Because these two are together connected to the sheath. That's why we are left with only this one. And this is point A, this is B point, this is point B, and it is C. This is point B. So CC, CC, and CS. These three are connected in parallel. Now it's clear. No? CC, again CS, again CS. Sorry, 2 CC and 1 CS. This is CS and this is CC. So how much will be this? Again, sorry, C. C and CS are confused. A and B. So how much is the capacitance between the two? All three are in parallel. So CA will be how much?
So 2cc plus CS.
Yes. CS we have already calculated 4, 2 CC, and CA is given as 10. So how much is CC? 10 minus 4 by 2. How much? 3, correct. So now substitute this here. 3 into 3 plus CS is 4. How much is this? 13 microfarad, correct. Yeah, so this is correct. Answer C. Is this clear? Initially there was some confusion. Now is this clear, right?
Yes, sir.
Part B. This B means these two conductors are connected together and also connected to the sheath. So this capacitance will also be this will disappear. All will be shorted. Everything will be short. This will be directly connected here. So now only these three capacitance are left. Okay, 13. Yeah. So I think we have exceeded the time. 2 questions are left. I will quickly just show you. You can do calculation. So a 22 kV 3-phase 50 Hz underground line 3.3 kilometer long uses 3 single core cables. Each has a core diameter of 3 cm and radial thickness. So diameter is given, we can find out radius, and insulation thickness also it's given. And permittivity is given, so we have to find out charging current. For charging current, first of all we have to find out the capacitance. Capacitance formula I told you 2 pi epsilon ln R by R. So R